In 1990, the Great Lakes ecosystem was officially declared a war zone. But the enemy wasn't a chemical spill or a factory. It was a mussel the size of a fingernail, costing the American taxpayer $500 million every single year. Yet today, the only thing keeping the entire system from total collapse is a fish everyone loves to hate. How did the most despised invasive species in North America become the only thing standing between us and an ecological catastrophe? The zebra mussel didn't just arrive in the Great Lakes, it conquered them. By 1988, these tiny, calcified invaders had effectively turned the water into a graveyard for native species. They filter feed with ruthless efficiency, stripping the water of the very phytoplankton that sustains the food web. But as the mussels multiplied, so did something else. A Ponto-Caspian intruder, the round goby, was lurking in the ballast water of cargo ships, preparing to change the trajectory of this entire aquatic war. And what researchers found next would completely shatter our understanding of natural invasive management. When the round goby was first identified in the St. Clair River in 1990, the reaction was immediate panic. Another invasive species was the last thing the Great Lakes needed. Scientists watched as the goby spread with terrifying speed, colonizing all 5 lakes in less than 5 years. They were aggressive, they were territorial, and they were everywhere. It seemed like a final death blow to an already suffering ecosystem. But then, the data began to shift. Researchers at the University of Windsor started noticing something impossible. The goby wasn't just surviving, it was feasting. In laboratory settings, they observed a single goby consuming up to 78 zebra mussels in a single day. This wasn't just feeding behavior, it was an ecological intervention that nobody saw coming. To understand why this is happening, we have to look at the goby's biological hardware. Most native fish are baffled by the zebra mussel. The shell is too hard, too sharp, and too tightly clustered. But the round goby is different. It possesses a specialized pharyngeal jaw structure, a second set of jaws, located in the throat, designed specifically to crush the calcified shells of Dreissonid mussels. This is a mechanical advantage that native species simply do not have. Even more impressive is the goby's sensory suite. They are equipped with free neuromasts on their heads. These are microscopic, hair-like sensors that detect minute vibrations in the water. In the dark, murky depths of the Great Lakes, while other fish are blind, the goby is hunting with total precision. They can navigate, locate, and dismantle mussel beds in conditions that would make most predators turn back. It is a biological superweapon, evolved in the Ponto-Caspian region to hunt exactly this kind of prey. And now, that evolutionary history is being put to the ultimate test in the heart of North America. But this isn't just about biology, it's about the massive financial burden that these mussels have placed on the region. The infrastructure cost is staggering. Zebra and quagga mussels clog intake pipes for power plants, water treatment facilities, and industrial manufacturing plants. They don't just sit there, they create massive, rock-hard colonies that cut off water flow, forcing companies to spend $500 million annually on cleaning and maintenance. It is a constant losing battle against a living, breathing blockade. Yet the goby has introduced a variable that engineers never accounted for: natural predation. While scientists were busy trying to poison the mussels or use high-pressure water jets, the goby was quietly performing a massive-scale removal operation. They are essentially acting as a biological filter. By consuming the mussels, they are keeping the population density in check, preventing complete blockages in areas where they established dominance. However, this raises a darker question. If we rely on the goby, are we just replacing one invasive problem with another? The answer lies in the delicate balance of the food web. As the goby consumes the mussels, they store the energy, becoming a high-protein food source for native predators like the smallmouth bass. The energy that was once trapped in the mussel's shell is now being cycled back into the ecosystem. It is a forced, artificial, but effective restoration of the energy flow. But as we look at the future of the Great Lakes, we have to ask ourselves, are we witnessing a permanent change or just a temporary pause before the next ecological collapse? But as we look at the future of the Great Lakes, we have to ask ourselves, are we witnessing a permanent change or just a temporary pause before the next ecological collapse? To understand why the round goby has become the most significant biological variable in the Great Lakes, we must look past the surface and into the tropic transfer. This is not merely a fish eating a shell. It is a fundamental shift in energy flow. Scientists at NOAA have conducted extensive, stable isotope analysis, a method that tracks the chemical signatures of food sources within an organism's tissue. The data is staggering. In some documented populations, up to 80% of a goby's diet consists exclusively of invasive drysonid mussels. This is an unprecedented level of specialization. Why does this matter? Think of the mussel as a biological vault. It locks away vast quantities of energy and nutrients in its shell, effectively removing them from the rest of the aquatic food chain. The goby acts as the key. Through the thermodynamics of predation, the goby possesses a metabolic efficiency that native benthic fish simply cannot match. They take the raw, locked-in protein of the mussel and convert it into high-density biomass at a rapid rate. This is the bridge. By consuming the mussels, the goby reintroduces that energy back into the ecosystem, making it available for higher-level predators like the smallmouth bass and the walleye. However, this bridge is double-edged. Because these mussels are filter feeders, they don't just eat algae, they concentrate toxins from the water column. When the goby consumes the mussel, it doesn't just ingest the protein, it ingests the pollutants. We are talking about the concentration of PCBs and other industrial chemicals within the benthic zone. This creates a localized nutrient sink, a hazardous hotspot of toxic accumulation that sits right on the lake floor. It is a biological paradox. The goby is repairing the broken energy chain of the Great Lakes, while simultaneously poisoning the very predators that rely on that energy. Every time a smallmouth bass strikes, it is gambling with a toxic payload. The scientists watching this process are not looking at a restoration project. They are looking at a system that is being forced to adapt to a new, chemically laden reality. We are witnessing the forced evolution of an entire inland sea, where the efficiency of the predator is dictated by the toxicity of the prey. The data is not just numbers on a page. It is a record of a system struggling to maintain its integrity against a tide of invasive bioaccumulation. The presence of the goby has triggered a cascade of systemic failures that reach far beyond the water's edge. Consider the mottled sculpin, a native benthic fish that once thrived across these lake beds. The goby did not just arrive, it displaced. By competing directly for spawning sites and food, the goby has forced the sculpin into rapid decline. This is not a slow replacement. It is a hostile takeover of the lake floor. But the crisis reaches into the sky as well. Researchers have identified a terrifying link between the goby mussel food chain and outbreaks of type E avian botulism. The mussels concentrate the toxin, the gobies eat the mussels, and the migratory birds, like the common loon, eat the gobies. The result is mass mortality events that leave thousands of birds dead on the shorelines. It is a direct, lethal connection between the bottom of the lake and the migratory flyways of North America. Despite this, the U.S. Fish and Wildlife Service classifies the round goby as a prohibited species. The problem? Eradication is fundamentally impossible. Once a population reaches this level of density, there is no chemical, mechanical, or biological method to remove them without destroying the remaining remnants of the native ecosystem. We are trapped. We have spent decades trying to manage the Great Lakes, yet we have allowed a scenario where our primary tool for energy restoration is also the primary vector for neurotoxins and biological displacement. The regulatory frameworks are essentially toothless. Laws prohibiting the transport of gobies are vital, but they cannot address the billions already thriving in the deep basins. We are looking at a permanent, irreversible change to the Great Lakes' biological infrastructure. The ecosystem is no longer the one we mapped in the 20th century. It is a new, synthetic construct built on the back of an invasive species that refuses to yield. As we evaluate the true cost of this environmental shift, we are forced to confront an uncomfortable reality. The very species we despise is now the only thing holding the remaining pieces of the food web together, even as it accelerates the collapse of the native order, a tension that sets the stage for the final, inevitable confrontation. If we cannot eradicate the invader, we must outsmart it. The shift in strategy from eradication to containment represents a brutal admission of defeat, yet it has birthed a new era of precision biology. Enter environmental DNA, or eDNA. This is not science fiction. It is the invisible fingerprint left behind by every living organism in the water. By sampling a single liter of water from the Great Lakes, researchers can now detect the presence of round goby genetic material long before a physical specimen is ever caught. This is the primary tool of the Great Lakes Restoration Initiative. It provides a real-time heat map of invasion fronts, but detection is only half the battle. The United States Geological Survey is currently pushing the boundaries of chemical warfare. They are developing selective pesticides, poisons engineered to target the unique biological receptors of the goby while leaving native species like the walleye or yellow perch untouched. This is surgical intervention. We are moving away from broad-spectrum toxins that poison entire bays. Instead, we are looking at pheromone-based traps. By synthesizing the chemical signals gobies use to congregate, scientists can lure these fish into concentrated zones. It is a trap set by nature itself. Yet, the most surprising turn of events comes from an unlikely quarter, the commercial sector. For years, the goby was considered trash biomass. Now, fisheries are exploring the use of these fish as a high-protein source for aquaculture feed. We are effectively attempting to turn an invasive plague into a commodity. If we can create a market for goby-based feed, we create an incentive for their removal. It is an application of integrated pest management that prioritizes the protection of native spawning grounds above all else. This approach acknowledges that we are no longer managing a wild wilderness. We are managing a high-stakes industrial facility where every calorie and every predator counts. We are no longer trying to turn back the clock to the 19th century. We are building a defensive perimeter around the remaining native order, using the very technology of the 21st century to hold the line against a biological tide that refuses to stop. The question remains, is a technological fix enough to counter a biological reality that is already embedded in the sediment? The crisis in the Great Lakes is not an isolated event. It is a mirror reflecting a global systemic failure. The round goby has now migrated into the Baltic Sea and other European waterways, tracing the exact same trajectory of destruction it pioneered in North America. This is the footprint of global trade. Every ship that crosses an ocean acts as a massive, floating biological syringe, injecting species into environments where they have no natural enemies. The economic fallout is staggering. We are looking at a documented loss of $200 million annually in recreational fishing revenue alone. This is not just a loss of fish, it is a loss of regional identity, tourism, and local economies that depend on the stability of the aquatic order. In response, The International Maritime Organization has tightened ballast water management regulations under the D2 standard, forcing vessels to treat their water before discharge. But policy moves at a glacial pace compared to the speed of biological invasion. Global trade routes remain the primary vector for these secondary invasions, and every new port opened, every new shipping lane carved, acts as a new front in this war. We have reached a point where international maritime policy is fundamentally incapable of keeping pace with the logistics of a globalized world. The Gobi is a symptom of a larger, more volatile system. It forces us to confront the fact that our economic infrastructure is tied directly to the degradation of our natural infrastructure. The cost of this oversight is measured in billions of dollars and the permanent alteration of global biodiversity. As nations scramble to protect their domestic waters, we see the rise of a new kind of environmental protectionism, one where the border is not defined by lines on a map, but by the genetic integrity of the water itself. We have built a world where everything is connected, and in doing so, we have made it impossible to keep anything apart. The final confrontation is no longer just about the fish. It is about the structural integrity of a global system that has traded ecological stability for the efficiency of the cargo container, forcing a reckoning that will reshape the next century of environmental law. As we cast our gaze forward to the next century, we must abandon the notion of restoration. The Great Lakes are not merely recovering from an ailment, they are evolving into a new biological reality. Scientific modeling suggests that the round Gobi is currently in a state of rapid colonization, but this will not last forever. Within the next 50 years, the system is expected to hit a steady state equilibrium. This is not a return to the pristine waters of 1987, but a stabilization where native predators, smallmouth bass, walleye, and lake trout finally integrate the Gobi into their dietary rotation. The predator-prey relationship is recalibrating, shifting from an unchecked explosion of biomass to a managed, albeit altered, ecological cycle. Yet this stability comes with a caveat. Climate change is actively rewriting the thermal map of North America. As the waters of the Great Lakes warm, we are seeing the northern limit of the Gobi's range begin to creep upward. Researchers now hypothesize that these fish will eventually migrate into the subarctic lakes of northern Ontario and Manitoba, regions previously shielded by their colder, more hostile temperatures. This is the new normal. The thermodynamic structure of the Great Lakes has been fundamentally rearranged by the zebra-mussel-goby axis. The mussels filter the water, increasing clarity and light penetration, which in turn alters the temperature gradients of the lake bottom. The Gobi, acting as the primary conduit for energy transfer between these mussels and larger fish, has locked this new state into the geological record of the region. We are witnessing a transition from a system defined by its historical indigenous baseline to one defined by anthropogenic disruption. The era of eradication is over. It has been replaced by the era of adaptation. We are no longer trying to remove these species. We are trying to understand the resilience of the ecosystem they have forced into existence. The future of the Great Lakes will be defined by our ability to manage this hybrid environment, where the invasive is no longer an intruder, but a permanent structural component of the food web. We have created a new thermodynamic reality, and we are now forced to live within the parameters of the world we have inadvertently built. The story of the round Gobi is not merely a tale of a small, aggressive fish invading a foreign port. It is a mirror held up to the globalized machinery of the 21st century. We began this inquiry by asking how a species Americans once despised became the primary engine of a biological shift that shocked scientists. The answer lies in the realization that the Gobi was never the true culprit. It was the mechanism. The true catalyst was a global shipping network that erased the distance between continents, effectively shrinking the planet until the Atlantic Ocean was no longer a barrier, but a bridge. We have learned that the Great Lakes, once thought to be vast, impenetrable wilderness, are actually fragile nodes in a global logistics chain. The steady state we predict for the next century is a testament to nature's relentless drive to find balance, even in the ruins of human oversight. The zebra mussel provided the foundation, the goby provided the bridge, and the shipping industry provided the vector. What happened next did not just shock scientists, it forced them to rewrite the textbooks on invasive biology and ecological succession. We have reached a point where the only path forward is to accept this permanent alteration. The ecological stability we once took for granted has been traded for the efficiency of the cargo container. As you look at the Great Lakes today, understand that you are not looking at a wild, untamed expanse, but a highly managed, anthropogenically altered system that will define the environmental policy of the next 100 years. The history of the goby is the history of our era, a collision of commerce and nature where the aftermath is irreversible. If you found this deep dive into the mechanics of our changing world insightful, consider subscribing to our channel for more investigative breakdowns on the systems that shape your life. Click the link below to join our community of analysts and let us know in the comments. In a world where global connectivity is inevitable, what is the price of our ecological integrity? We look forward to your perspective.